Thanks for introduction. My name is Zhicheng. I'm a second-year PhD student from Renmin University of China. Today's topic is competitive information design with asymmetric senders. And this is a joint work with Tang from Columbia University, Zihe, Wang, and Shuo from Renmin University of China. And by the way, two of my co-authors, Wei and Zihe, are also here. And remember to take some photos for me. Thanks. Okay, let's start with an example of sales competition. There is one buyer who wants to buy only one new phone with the best quality, and there are two sellers in this market. And both sellers can design various advertising strategies to influence the buyer's belief and thereby increase their winning probability. Let's look at the picture. The left seller said, "Buy my phone and enjoy the convenience of his lightning fast charging," while the right seller says, "Buy my phone and take amazing photos with its high-quality camera." We can see that both sellers reconstruct their information and promote their products from the different perspectives, highlighting their strengths and avoiding their weaknesses to maximize their winning probability. So this is an example. This example can be summarized as competitive information design. And we also have other applications such as clinical trials competition, election campaign, and so on. Also, we should notice that asymmetry arises naturally in competition because multiple competitors are likely heterogeneous with different information, abilities, and characteristics. Okay, this is the outline of our talk. First, I will introduce our model. Second, I will provide the sufficient condition for equilibrium existence. And third, we will provide the necessary and sufficient condition for equilibrium when an equilibrium exists. Fourth, we will solve for general two-sender game and fully characterize the equilibrium. Okay, here we introduce our model. There are n senders with xn heterogeneous prior, and n is equal to or bigger than 2. Each sender I has a quality value, Vi, which is independently distributed by a prior belief Fi, and Fi is a cumulative density function over the interval 0 to 1. And there is only one risk-neutral receiver. The senders and the receiver engage in a multi-sender version of Bayesian persuasion. We all know that this classic model was first introduced by Kemanica and Gensico 2011. And the multiple senders send information regarding their own respective real estates. The receiver updates the posterior belief for each sender I according to the Bayes rule and chooses the action that maximizes her expected utility. So the timing of our game is, first, each sender I commits to use a signaling scheme in which pi I represents a conditional distribution of signal, and Si is a signal space. We know that the receiver is risk neutral, and she will only focus on the expectation of sender's posterior belief. So we can reduce each sender's information strategy to the MPC space. That is, our first step becomes that each sender I chooses an information strategy Gi belonging to MPC of Fi. Next, let's see what is mean-preserving contraction, shorted as MPC. According to this lemma, a distribution G is an MPC for some prior F if and only if all t belong to 0 to 1, the following inequality holds true, and the inequality holds at equality when t equal to 1. More importantly, this lemma also says that given any prior F, the space of all feasible information strategies is equivalent to the MPC space. For easeful understanding, we provide an example of MPCs. And in this figure, the blue curve represents the prior distribution, and both these two right curve represent an MPC of the prior F. Okay, let's back to the timing. After choosing a strategy Gi belonging to MPC of Fi, each sender I realizes a value via tilde according to their strategy Gi. And then the receiver observes all the realized value and chooses the maximum value under the uniform tie-breaking rule. This means that when indifferent between multiple senders, the receiver will choose one uniformly at random. Okay, as for the sender's utility, if chosen by the receiver, sender I will get utility 1, and otherwise the utility is 0. Okay, what's more, given any strategy profile Gi, G minus I, sender I's expected utility is the expectation of the interim utility function UIX. And the UIX represents the probability of beating all others when drawing a value of X. And the solution concept we focus on is the Nash equilibrium. Just like the standard definition of the Nash equilibrium, a strategy profile, Gi star, G minus star, is an equilibrium if and only if each sender strategy, Gi star, is the best response to other strategy, G minus star, that is the following an infinite dimensional linear program. Okay, next, let's talk about our related literature. Our model basically follows the framework of Bayesian persuasion and information design. In specific, our model is a special variant called competitive information design. In the basic setting of Bayesian persuasion, there is only one sender, while in the setting of competitive information design, there are multiple senders, all of whose information affect the receiver decision, and all senders' interests are not aligned. So there is some relationship of computation and collaboration between the multiple senders. And further, we can divide it into two categories. The first is common state realization, which means that multiple senders send information regarding their common realized state. And the second is independent state realization, which means that multiple senders send information regarding their own respective realized state. Okay. Our paper falls into the second category, and among this, the most related two papers focus on the symmetric setting of the setting competitive information design. Well, the computation with XN asymmetry is less studied in this area. So we fix its problem, and our paper can be seen as an extension from the symmetric setting to the asymmetric setting. And the introduction of asymmetry has changed many existing results and posed technical challenges for us. Okay, maybe is there any question about our model? Okay, great. Next, let's talk about the equilibrium existence. Previous work has already shown that an equilibrium always exists when all senders have symmetry prior, or we can say in any symmetric setting. So here comes the question, what about asymmetry? Does equilibrium existence always hold true in any asymmetric game? The answer is no. Here, we provide an example to show no equilibrium when there is a mass in senders prior. And we consider a two-sender game. Sender 1's prior F1 is a uniform distribution from 0 to 1, and sender 2 is a degenerate distribution. And according to the definition of MPC, sender 2 will always use the strategy F2, and under the uniform tiebreaking rule, facing the strategy F2, sender 1 has no best response. So there is no equilibrium in this game. Okay. Here is a sufficient condition for equilibrium existence. An equilibrium exists if there is no mass in all senders priors. Okay.
Have you considered different tie-breaking rules?
Yes.
Like our allowing to choose the tie-breaking rule with the equilibrium?
Yes, that's a good question. Our results also hold for other tie-breaking rules. So we use the uniform tie-breaking rule just as an example.
Okay.
Okay, thank you.
So what if there are two distribution and two mass points? I mean, they are the same, but just two deterministic distribution.
Okay, this may be an equilibrium because both the two senders will only have one feasible strategy, so they can't deviate to other strategies. So this is an equilibrium.
Yeah, I think if distribution are the same and they have some mass point, if they are, so if all distributions are discrete, have mass points.
Yes.
I think in this case, this still exists this equilibrium. I'm not sure, just some conjecture.
Maybe we can talk it later. I can have an immediate answer for you. Thank you. Okay. Here we provide the challenges to prove the Nash equilibrium existence. First, the existence of the symmetric equilibrium is established directly through a construction method. Well, in the asymmetric setting, the direct construction is impossible because each cylinder has a different MPC space, faces a different optimization problem, and may use different strategy in equilibrium. Second, all the existing results regarding the equilibrium existence don't work. Our game is a kind of discontinuous game, which means that each player has an infinite action space, but maybe discontinuous utility because of tie breaking. So for discontinuous game, there are two main technical approaches to achieve the equilibrium existence. The first is approximating through finite game, a sequence of finite games, and the second is approximating through a sequence of continuous game. Our proof method follows the general idea of the first approach, but we have added some special treatment to the MPC constraints. Because each cylinder's action space is an infinite dimensional space with an infinite number of constraints, so we can't directly discretize the action space. Okay, so how do we achieve the equilibrium existence? Our key proof idea is the discrete approximation and passing to the limit, which can be summarized into these three steps. In step one, we construct a sequence of finite games through discretizing the action support and the MPC constraints. Then we directly apply the Nash theorem and obtain a sequence of discrete equilibrium strategies. We should notice here, in each finite game, each cylinder's discrete equilibrium strategy, GIN, may not be a valid MPC of the prior Fi. However, in step two, we can prove that this sequence has a subsequence that weakly converges to a certain distribution Ji star, which is indeed an MPC of his prior Fi. In the last step, we prove no discontinuity in all cylinders' utility, so we can establish the convergence of utility along with the convergence of discrete equilibrium strategies. And these four figures above show the convergence of discrete equilibrium strategies. When passing to the limit, these discrete distributions converge to the red curve in the fourth figure, which is indeed an MPC of its prior Fi. Okay, after establishing the equilibrium existence, here we want to talk about the equilibrium characterizations. First, we should understand each cylinder's best response problem, and thanks to the Walktrack and Martini 2019, there is a very useful tool to verify this kind of best response problem. And we know if there exists such convex function phi that satisfy all these four conditions, then the certain distribution G is a best response to the function Ux. However, it is unclear how to construct such convex function phi. And in our paper, we construct such convex function phi for each cylinder I using the equilibrium property. In detail, we introduce the concept of a virtual competitive function, shorted as VCF, to serve as such convex function phi for each cylinder I. And here we'll provide a brief introduction of the construction method. Given any strategy profile, Gi, G minus I, and we consider each cylinder I, there exists a partition that divides the whole interval 0 to 1 into multiple pieces, and within any piece, the interval Vk to Vk plus 1. One of the two cases hold true. Case 1 is that Gi coincide with the prior Fi everywhere, and phi I also coincide with the function G minus I everywhere within this interval. And the case 2 is that Gi doesn't coincide with the prior Fi, while phi I is linear over this interval. Okay, with the construction of the virtual competitive function, we can here provide the necessary and sufficient condition for equilibrium. The strategy profile G1 to Gn is an equilibrium if and only if for each cylinder I. First, the VCF phi x is equal to or bigger than G minus Ix for any x belonging to 0 to 1. Second, the VCF phi I is convex over the interval 0 to 1, and there is no x belonging to 0 to 1, at which Gi and G minus I are both discontinuous. And we want to provide some intuition about this theorem. This theorem guarantees that when fitting the VCF phi I, GI has no incentive to contract or spread based on his current strategy. That is, GI best respond to the VCFI, which implies that GI also best respond to the function G minus I, and further implies that GI finally best responds to the interim utility function UI. This theorem serves as a very useful tool to verify equilibrium. And using this theorem, we achieve the following proposition regarding the non-uniqueness of the equilibrium. Okay, here comes to our last section, applications. We use all the equilibrium characterizations shown before to solve for a general two-cylinder game, in which both cylinders prior are strictly unimodal. This means that the prior distribution is first strictly convex, then strictly concave. And this definition includes many canonical distributions, such as normal, triangular, beta, and so on. So here you may wonder, what is the equilibrium structure like? I'm going to answer this question. And most importantly, the competition between the two cylinders result in the structure of a conditional uniformity, which means that both equilibrium strategies are uniform at high values. And based on whether the local MPC boundary points are aligned, we divide the structure into two types. The first is synchronous conditional uniformity, shorted as SynCU. The second is asynchronous conditional uniformity, shorted as ACCU. And any feasible MPC can be composed of multiple local MPCs. In this figure, the points 0, x1, x2, x3, and 1 are all local MPC boundary points. And why the structure of conditional uniformity? According to the results shown before, we know that G1 and G2 are both convex and continuous over some interval, total 1. And over any subinterval of total 1, one of the three cases hold true. Case 1 means that one strategy is strictly convex while the other is linear. This is impossible because the cylinder with the linear structure can have a profitable spread. So only the case 2 and case 3 can hold true. And we can see that both equilibrium strategy maintain aligned, either both strictly convex or both linear. Okay, this is an example of the SynCU structure. The left figure represents cylinder 1, the right figure represents the cylinder 2. Both the blue curve represent the prior distribution, and the right curve represents the equilibrium strategies. Okay, we can see from these two figures that both cylinder equilibrium strategies coincide with their respective prior up to the same point A, then follow a linear structure over A to 1. So this is a SynCU structure because the local MPC boundary points are all aligned. Okay, this is an example of the ACCU structure. We can also say from these two figures that both equilibrium strategies alternately form local MPCs over total 1 and also exhibit a linear structure. And the local MPC boundary points are not aligned. So this is the structure of ACCU. Okay, for summary, our contributions can be summarized into 3 points, and we also provide some future directions, such as combination with prior decision, complexity of verifying equilibrium, equilibrium computation, and so on. This is the QR code of our paper, and feel free to contact me at this email address. Thank you.